Okay, we're going to talk about evaluating integrals over ellipses. And this is to be contrasted with integrals over circles. So if you have a circle, or a disk really, you can just use polar coordinates, right? Because you can just parameterize this by r and theta. But if you have an ellipse, polar coordinates don't work very well. They actually make the problem harder. So it would be a bad coordinate choice. But there's a very elegant way to get around this, and it's just by rescaling. So for example, let's evaluate the integral of y squared over our region R, where R is enclosed by the ellipse, let's say 9x squared plus 4y squared equals 1. I think the first step is just to draw the ellipse to see what we're working with. And which way is shorter than the other? It turns out the x is actually the shorter side. This is exaggerated, not to scale. But the reason that x is the shorter side is because if you plug in y equals 0, you get 9x squared equals 1, x equals 1/3. And so that means, of course, in a similar way, if you do x equals 0, you get y equals 1/2, which is larger than 1/3. Okay? So this is the ellipse, but what we really want is a circle. So we want a circle, so we're going to write a good change of variables such that u and v, they yield a circle. So here's one way that you can do it. Just argue that 9x squared is 3 squared x squared, so really it's just 3x squared. Similarly, 4y squared is 2y squared. That is, let's see, 3x squared plus 2y squared equals 1. This suggests letting 3x equal u and 2y equal v. You could also, alternatively, just let 9x squared equal your u squared. That's what we want. 4y squared equals v squared. That's what we want. And then just solve for u by square rooting. Okay, so that's our u substitution, or change of variables. So that is 3x equals u, and 2y equals v. Okay, so by construction, this gives you u squared plus v squared equals 1. That's our ordinary unit circle. Okay, so that means if we just call this region R bar, and this came from R, which was our ellipse, then the integral of y squared over R, and I'm going to now replace this with a dx dy, this will be equal to the integral over R bar, and then we have y squared, which is, if we solve for y, this is v over 2, so now it's v over 2 squared times dx dy. So now we just need the Jacobian, right? Because x equals u over 3, so now this is du over 3 times dv over 2. So the Jacobian is 1/6. So our integral is now something over a circle. This particular integral is easy because now you can use polar coordinates. Remember, this r bar is just the unit circle. So now we can use polar coordinates. What we do is just let u equal to r cosine theta, because u serves as our rescaled x, and v equals r sine theta. And then this v squared, it'll just turn into r squared sine squared theta, and these are good. Okay? So let me just do another example of how to set up another integral over ellipses. So let's take the integral over our region R of sine of 9x squared plus 25y squared dA. As soon as you see 9 and 25, you should immediately think these are squares. And the region R will be, it'll be enclosed in the first quadrant and bounded by the ellipse 9x squared plus 25y squared equals 1. See, and notice the parallel with the integrand. You won't really see anything more complicated because then it would be impossible. So remember, whenever you see something that's hard, know there's always a trick, and the trick here is that these are the same. So it'll turn out that this will be your r squared and this will be your r squared, and there will be an r dr d theta after you change variables, and so that'll let you do it. Anyways, as before, I would just draw the ellipse. So when you set y equal to 0, you get 9x squared equals 1, x equals plus or minus a third. And similarly, if we hit x equals 0, you get y equals plus or minus a fifth. So the y is the short side. Okay, so now what you do is you let 9x squared equal u squared, because we want to turn this into a circle. And then we want 25y squared equal v squared. And of course, that just means 3x equals u, or x equals u over 3, and 5y equals v, or y equals v over 5. And so the Jacobian dx dy will get 1/3 times 1/5 du dv. The Jacobian is 1/15. Okay? And so now our region R, now it becomes just an ordinary unit circle. So our integral over R of this sine we conclude after transforming, it's an integral over R bar of sine of u squared plus v squared, and then we have our Jacobian 1/15, and then we have du dv. And so now I would again use polar coordinates. U equals r cosine theta, v equals r sine theta. And what you eventually get is sine of r squared times 1/15 times r dr d theta, and r times sine of r squared, that's good. Right, because this is just negative ddr of cosine of r squared, and I think there's a 1/2 somewhere. So then you can just integrate that thing. Okay, hope this was useful. Thanks for watching.